Texture mapping. Anybody know what texture mapping is? Anybody heard of it before? You might have heard of texture mapping. Those of you who play a lot, perhaps play computer games, have heard about texture mapping. Okay. Essentially, what we're doing is we're taking a two-dimensional image and mapping it onto a three-dimensional polygon. So one thing I want you to sort of remember is your screen space, which after we've done all the projection is in that unit cube, is a three-dimensional space. We just happen to look at it along the z-axis, so it looks like a 2D space. So screen space is actually a 3D space. And when we project it onto the screen, we're just looking at it from a 2D perspective. Okay, so texture mapping, you're taking an image, usually that image could be, for example, a photograph or a pattern or something like that. And we want to map it onto a polygon. So let's say you're creating a virtual world and you want to have a brick wall. So let's say one side of your house in your village you want to show as a brick wall. You could have a polygon for each brick. Okay, but you'll end up with thousands and thousands of polygons. It's easier to go out and take a photograph of a brick wall and then sort of virtually paste that photograph onto a single polygon. Okay, so that's what we're going to be looking at doing. The image which is mapped onto the polygon is what we call a texture. Okay, so when I refer to a texture, I just mean a two-dimensional image. That image is what we refer to as a bitmap. Right, guys? At 2:05. Okay, so I mentioned that image is called the texture. Okay, and that's a bitmap. That is in itself a type of raster. But what we do to distinguish between a pixel in the texture and a pixel in the raster, we call a pixel in the texture a textile. Okay, textile just means a pixel from your raster. So if you go out and take a photograph, that gets digitized. Each sort of that's in itself is a bitmap or a raster. Each pixel within that photograph, we call it a textile. So pixels mean what's the pixel on your raster, which is on your screen, and textiles just a pixel within your texture. So what we do is we look up the color of a textile. Okay, so for each pixel we say, okay, what's the equivalent pixel in the textile or equivalent textile in the texture? And then we just say, okay, that pixel assumes that color. Okay, so this is sort of diagrammatically speaking what we do. So we have a texture. So I've got a smiley face texture here. We refer to this texture as being in its texture space. So note, we use U and V. Okay, sometimes it can be confusing because U's, V's tend to look like U's and vice versa. So your texture space is a 2D space with U, your horizontal axis, V, as your vertical axis. Okay. Then, of course, you have your world space. Okay, so world space is a line, so your polygon, you're looking along the z-axis at your polygon. Okay, and then this is projected onto your screen space. And remember, your screen space is 3D, but when we look at it along the z-axis, all we see is the x and y axes. The z-axis is sort of into the screen, but we have a 2D screen, so that's what's projected onto our 2D screen. Okay, so that's essentially the process of texture mapping. We want to put this smiley face onto this coordinate so it shows up on our screen like this. Okay, that's quite simple to say. It's a bit more tricky to actually do. Okay, so just talking a bit more about this texture space. It's a 2D space where the texture exists. Okay, the horizontal axis in the texture space is denoted by U. The vertical axis is denoted by V. And these are all in the range 0 to 1. Okay, so the origin of the texture space is 0, 0. This point down here, that has U and V coordinates 0, 0. The top right sort of corner has coordinates 1, 1. So U and V are in the range 0 to 1 and 0 to 1. Okay, a texture map will fill that texture space. So it doesn't matter what size of map you have, it always gets sort of scaled sort of 0 to 1 in both directions. Okay, so if that's our texture space, we have lots of sort of textiles defining our texture. We can calculate the coordinates of each textile. Okay, so in this case, in order to distinguish from the raster from the texture, I'm using MX and MY to be the number of textiles in our texture, rather than NX and NY as number of pixels in the raster. Okay, so if you've got the U coordinate, so let's say you've got your U coordinate, which is somewhere between 0 and 1. Okay, add 1, multiply it by MX, add 1 to it, and find the floor. Okay, so can you see that sort of these braces have just got, they haven't got like a top, but they have got a bottom. Okay, that means the floor. So it means round down to the nearest integer. Okay, and do the same for the V coordinate. So big U and big V should be natural numbers. It should be whole numbers greater than 0. Okay, so if your texture has 100 by 100 textiles, and you have a U and V coordinates, which are 0 to 1 and 0 to 1, all you do is multiply them by 100, add 1 to it, round down. Okay. This adding 1 to it always ensures that you never have a 0 textile. It always starts at 1 and ends at, for example, 100. So when U is equal to 0, then big U will be equal to 0. And when U is equal to 1, big U is equal to MX plus 1. So sometimes we have to do a check to ensure that our U coordinate isn't exactly 0. So sometimes we do a little check. If it's 0, we just add a tiny amount to it, just to bump it up a bit. Likewise, if U and V is exactly equal to 1, we subtract a very small amount from it, just to sort of ensure that when we calculate big U and big V, they're not greater than or less than what we have. Okay. So for example, here's a snippet of a Matlab program. By the way, you're never going to have to sort of code this in Matlab. It is quite an involved thing. So I just show you for completeness. So let's say U is less than 1d minus 6. That means 1 times 10 to the minus 6. So that's 0.5 noughts and a 1. So quite a small number. So if U is less than that, I just set U to be that small number. Likewise, if U is greater than or equal to 1 minus 1 times 10 to the minus 6, I set U equal to that. So that's U being set to 0.999999. I think I've got the right number of 9s there. Okay, so it just means it's not quite, it's a bit bigger than 0 and a bit less than 1. It's just a check. Okay, once you've done this sort of, this thing, find the integer values. So MX, that's the size of your texture. Multiply it by your U, which is going to be somewhere between 0 and 1, plus 1 to it, and that will give you your big U, and similar for big V. Okay, so that's textile coordinates. That's taking your texture space coordinates, little u and little v, and determining what the coordinates of the textile are. Okay, so how do we apply a texture map? Well, on the left I have our texture space, and on the right I have our screen space. Now in your screen space, your polygons aren't always going to be sort of parallel to the x and y axes. Some, they're going to be sort of skewed and sort of moved around as you move your viewpoint around your world space. Apply projection, apply a perspective, things things are going to get sort of shifted around a bit. So let's say we have this sort of polygon here. What we do is we have like an anchor point. So this polygon has vertices P1, P2, P3, P4. And what I'm saying, and this is what we define, is we say P1, this point here, corresponds to the origin of our texture. It's like an anchor point. Okay, so if I was to rotate that polygon, okay, that point, wherever it ends up, is still anchored to the origin of the texture map. Okay, so if P1 corresponds to Q1, P2 corresponds to Q2, P3 over here corresponds to Q3, and P4 corresponds to Q4. Okay, so there is a sort of a mapping, a corresponding mapping between the corners or the vertices of the screen space polygon and the vertices of the texture space. Now we saw when we looked at filling, okay, we go down in horizontal rows, okay, scan line. Okay, you start at the top, you do all your top row pixels, then you move one row down, you do the next row, etc. So scan lines go from top to bottom horizontally. So let's say we have this scan line here. Okay, so this is in the screen space, this dashed red line corresponds to that scan line. PL and PR are, remember, we call these scan extrema. So it's where your scan line intersects with the edges of your polygon. Okay, so you calculate PR and PR, they're just linearly interpolated between the corners of the polygon. And what we do is we determine what are the corresponding points in the texture. So if we look at PL to start with, PL is somewhere between P4 and P1. So remember, P4 corresponds to Q4, P1 corresponds to Q1. So it's going to be somewhere down this edge. Okay, so this sort of, I think this is about halfway. So PL is about halfway between P4 and P1. So QL would be halfway between Q4 and Q1. On the other side, we have PR. Okay, now PR intersects the polygon on the top edge. You see the polygon's just been sort of twisted around a bit, just been rotated. So PR intersects on the top edge. So QR is going to be on the top edge of our texture. So here we see PR is quite close to P3, so QR is going to be quite close to Q3. Okay, so the scan line on the polygon, which is horizontal between the scanning extrema PL and PR, has an equivalent scan line on the texture between QL and QR. But you can see this scan line isn't horizontal. Okay, it's corresponding to that horizontal scan line there. And what we do is as we go across the pixels of our scan line, we go across the textiles of this scan line. And for example, here we have a black textile where it's near the eye, and therefore we'll have a black pixel there corresponding to where the eye is. Okay, so you can see there's sort of a mapping between your screen space and your texture space. And that slide's pretty much summarizing what I just spoke about. So your vertices in your polygon P correspond to the vertices of the texture Q. Okay, so any transformation on the polygon should be accounted for by the texture mapping. So as the polygon is rotated, okay, that texture map should also rotate on the screen. The texture map in the texture space stays as it is. It's just the mapping applied on the screen. So we use the scanline method, horizontal scan lines, find out where the scan extrema are, where your scan line crosses your edges of your polygon, determine the equivalent edges or the equivalent scan extrema in the texture, and then interpolate between them. Okay. So that pretty much summarizes what I just spoke about. It's kind of easier said than done. Okay, in a sort of, if I was to ask you a question in the exam, that's what I'd want. That's sort of the description I want from you. To actually do it using mathematics, it's kind of involved, and we're going to step through that in today's lecture. Okay, so the first thing we've got to do is our vertex coordinates. Remember, the screen space is in a unit cube, -1 to +1. After we did, remember, if you've done the clipping assignment, you have that projection matrix that scales everything to a unit cube. So what we do is the first thing we need to do is calculate the pixel coordinates of your vertices. So what we do is we add 1 to the screen space coordinates, multiplied by the number of coordinates in the x direction, divided by 2. Okay, and that is your pixel coordinate. This max 1, comma, that expression, that just makes sure that it's never less than 1. So we can never go down to 0. And similar for y. Your y coordinate +1 multiplied by half the number of pixels in the y direction. Your scan extremer, PL and PR, are initialized to the vertex with the largest y coordinate. Okay, so whatever the top one is. If I just go back a slide, so P4 would be our starting point. So you look for the top coordinate. Sometimes your polygon will be flat on the top, and you just choose one of the two that it's flat on. Okay. The y coordinate of PL and PR are calculated for each scan line by subtracting 1 from the previous coordinate. So the top scan line for that polygon would be the top vertex. The next scan line down would just be -1 from that. Okay, the tricky thing is calculating the x coordinates of the scan extremer. Okay, and we just interpolate. So in this case, if this was my rotated polygon, okay, my left scan extremer, PL, is somewhere between P4 and P1 at this point. If the scan line was down here, it would be between P1 and P2. But let's say it's between P4 and P1. Okay, so you take your x coordinate of P4 minus, and here we have the distance between the top coordinate and your current scan line, y. So y is the coordinate of the top vertex. Y on its own is the coordinate of the scan line. That's divided by y4 minus y1. So it's kind of like the proportion. How far down that edge are we? And you multiply that by x4 minus x1. So it's like multiplying by a proportion. But since your y coordinate is simply whatever for the first time, okay, so let's say we're looking at the first scan line down, would be y4 minus 1. Okay, we replace that and it simplifies. Okay, so you just take your x4 coordinate and subtract that. And that's the inverse of the gradient. So rather than changing y over changing x, we have changing x over changing y. Okay, so this can be pre-calculated. This is constant for all the edge on your polygon. So all you have to do is subtract a number each time. Okay, so the left scan extremer is equal to the previous scan extremer minus some gradient. And I've called the gradient delta x. Okay, so delta x is just a shorthand. It's not the change in x. Sorry, it's not the total change in x. It's the change in x as we go down the scan line. And we're going to have different ones to the left and right scan extremer depending on which edges it intersects. So, for example, the right scan extremer will be between P4 and P3. If the scan line was to go down a little bit more, okay, on the left it will still be between P4 and P1, but on the right it will be between P3 and P2. Okay, so depending on which ones are intersected, depends on what your gradients are. Okay, so your left and right extremer points are calculated using simple linear interpolation. What are delta x? L and delta x are? Well, the left one would be width of left edge, that's on your polygon, divided by height of left edge, again on your polygon. And the XR, width of right edge, divided by the height of right edge. That will change depending on which edge of the polygon your scan line intersects. Okay, so what we have, this is a bit of a complicated diagram, so I'm just going to explain this. Let's say this is our polygon. Okay, so this is our polygon on the screen. This point at the top, okay, that's our starting point. So our X and Y coordinates are initialized to that one. And what we do is we go down each scan line. Okay, so let's say here we have a scan line. So this is has coordinates XL, so that's like the left scan extremer, and this one has XR. And both, because it's a flat line, have a Y coordinate. Okay, and that Y coordinate just goes down by 1 each time. Okay, well, on the equivalent one on the texture, okay, so this left edge, XLY, corresponds to ULVL. And XRY, the right scan extremer, corresponds to URVR. Okay, so that's our scan line in the texture. Okay, so what we have is, as this point goes down the left side of our polygon, this point in the texture must start at U4V4 and must end up at U1V1 when the scan line ends up at X1. So in this span, so the span between X4Y4 and X1Y1 should be equivalent to this span down here. So we go down in the texture to make sure that the spans are the same. And likewise, going across, so URVR goes across the texture in the same span as we go down this edge here. Okay. So VL, which is the left extreme point in the texture, goes between V1 and V4 and V1 in the same span that Y goes between Y4 and Y1. Okay, so therefore, okay, what we have is two expressions. So the change in V, okay, is V4 minus V1 divided by Y4 minus Y1. So for each pixel we go down, we're subtracting this from our texture space coordinates. And we also have the same for U. If you notice, if we're going down the left side, U, or delta U, is going to be 0, because we're not deviating to the left or right. Okay, so delta U is going to be 0, we're going down this side, but delta V is going to be some number. Like if we're going across the top, delta UR is going to be some number, but delta VR is going to be 0. So we only ever go on trace on the outside. So with delta UR and delta VR and delta UL and delta VL, one of them is going to be 0, one of them isn't. Okay, and all we do is we subtract whatever delta UL is from UL to get the next texture space coordinate. Okay, and similar for the right-hand side. Okay, so there's your interpolation equations. Okay, so we'll calculate delta U and delta V, depending on which edge we're at. And we just add that change to our U and V at every step. When we go across the scan line, okay, so this is where we're going across these pixels. So we've gone down the left and down the right to calculate the scan extremer. Now we've got to go across the middle. Okay, so every pixel we step across, we're going to add delta U and delta V to our U and V coordinates. Okay, so in the delta U and delta V are here. So notice it's the width of the texture scan line, so this width here, divided by the width of the polygon scan line, which is that width there. That's changing U, and changing V is the texture scan line height, which is this height, divided by scan line width. And there's your result. Okay. So this is, I'm going to show you, hopefully show you in a minute, a demonstration of this. Again, my picture of my cat. Okay, so that's 320 pixel wide by 240, I think, pixel high texture. So that's the texture map. That's my photograph. What I've done here is put it onto a polygon for a 400 by 300 raster. And I've done that using scanline. Okay, and there is some MATLAB code in the notes. It is quite involved. It took me a while to actually work out how to do it and how to program it. But if you're interested, you can have a look. I'm going to show you a demonstration of this now. So here I've got it. If I just make it the fonts a bit bigger for you. Okay, so what I've got here is just a quick program. It takes a polygon with these vertices. Okay, I project it and I've rotated it a bit, and then I apply a texture map. So if I run this, oops, I'm going to run that. Okay, well, I'm going to first run it for a photograph. And what I'm going to do is I'm going to rotate it around the z-axis, and I'll talk about perspective in a minute. There you can see I have that polygon applied or texture mapped, the texture map onto the polygon, and I'm rotating the polygon. I don't know why. I think I missed off a semicolon there, but you can see it's still maintaining the sort of shape of the image. Okay, so the texture map takes into account that the polygon is rotated, but it's still doing its job. Okay. Okay, cats tend to get a bit boring, so what I'm going to do, just to liven things up a bit, let's change the image. Really unlike me for doing this. Yeah. Works with any image you want to pick, you know, it will still work. So kittens are moving upside down. Okay. When we're sort of when people tend to demonstrate these, we tend to use chessboards. So that's why I've got a chessboard one here. Okay. So that's an 8 by 8 texture. So that texture is very small compared to the photographs are hundreds by hundreds texture. It's just an 8 by 8 texture. It still works, even though this raster is 200 by 200. It will still scale it up. So a texture map will scale it up or scale it down, depending on the size of your polygon. Okay. One thing I'm going to do is go back to Killian a bit. Okay, and this time I'm going to do it so the rotation's around the y direction. Okay, so this time actually I've got some, I think output in that P is slowing it down a bit. So where's P outputted and why is it? Oh, I know why, I was messing about a bit earlier. There we go. Just going to take that off. This code, by the way, is just the code which is in the notes. Yes, I did. So this time it's about the y-axis. So it's just sort of, I've rotated it. And you can see it sort of works a bit. It may look a little bit unrealistic. I don't know whether you can see that, but it's not quite sort of working. Okay. It's clearer if I use what we call an X motif. So what I'm going to do now is do the same thing, but this time I'm going to use an X pattern. That's an X. So the actual texture is just a straightforward X. You can see we've got something like it's curving round. Something's not quite right. Okay. So we've got to do something else. So after all that work, it takes you ages to write a texture mapper. It's not quite working. We have this sort of bowing or some skewness coming in. Okay, so this is what we call a linear texture map. There's a linear relationship between the scan line on the polygon and the scan line in the texture. Okay. Yeah, if you want, you can mess about just to show you, but it doesn't really matter what. Okay, so at the moment my raster is 200 by 150. Well, let's halve the number of polygons. Sorry, number of pixels. So I'll do it as a photo again. Okay, so you see, dropping the number of pixels makes it worse, but it still works. So that mapping is still, it just runs a bit faster because there's fewer pixels to have to mess about with. Okay. Sure Killian's liking the fact I'm using his image. So the output, it works. Okay, that code is all in the notes. Again, it's not particularly interesting, but it's there. Okay, and that's what I mentioned. We have this sort of skewing as we're sort of rotating the polygons back and forth. It appears to be sort of skewing. So what's gone wrong? Well, the problem is our texture mapper assumes the projection from 3D to 2D is a linear transformation. Now, as I mentioned at the beginning of this lecture, the screen space is still a 3D space. We're just looking at it from the point of view down the z-axis, so we don't see any z-axis. So what happens is when our polygons are rotated and we have perspective applied, is part of the polygon is further away than other parts. But our linear texture mapper doesn't take that into account. So in the middle bullet point there, the relationship between our x and our x and y and our screen space x and y is linear, but z is not. We've still got a z coordinate there. It's just we're looking down the z-axis, so we don't use it. So in order to fix the texture mapping, we need to take into account the distance of the viewer into account. Okay, so we're going to take into account perspective projection. Okay, so to explain this, I've got this diagram. This is meant to be an eye. Okay, and eye is looking down the z-axis. Okay, and here's the x-axis. So if I was to turn that up, sort of x, if I was to sort of rotate that, x would be going from left to right as usual, but I've done it this way. Okay, and let's say I have 2 points. Okay, x1, y1, z1. So these are world space coordinates, and x2, y2, z2. Okay, so let's say that's a polygon which is at an angle. Okay, using the projection plane, so we have a plane at some distance along the z-axis, and we draw projectors from the viewpoint to our vertices, or to our points in the world space, and where they cross the projection plane, we have our projected screen space coordinates. Okay, so even though they're projected onto a 2D plane, when we divide using homogeneous equation by that fourth number, we have a 3D screen space. Okay, so this is assuming, I mean, what we have here is our Z value is F. Okay. Now, this is sort of repeating a bit what Killian said in the first term. If P is a point in your world space, PS is the equivalent projected point in your screen space. Okay, these are the projection equations. So essentially, the distance from PS to A divided by O to A is going to be the same as P to B divided by O to B. So that's where these come from. So XS over F is the same as X over Z. So if I rearrange that, XS is equal to F over Z times X. Now that's bog standard perspective projection. And similar for Y. So if you look at an equation of a line in the world space, okay, let's say X equals alpha Z plus beta. So I've got an equation in an XZ space. Okay, so remember Z is pointed away from you. X is sort of, in this case, X is the vertical axes. If I replace X with our perspective projection in terms of XS, okay, and then I rearrange to make Z the subject. So what I've done there is I've said, okay, that's my equation in the world space. That's a line in the world space. Let's project that onto the screen space, and I've done that. I said, what's the relationship between the depth and a lateral distance? So remember, x is some lateral distance, z is depth. What's that relationship? And we get this equation here. The key thing is here, beta and f, they're just numbers. Beta over alpha, again, just numbers. The key thing is here, our independent variable is on the bottom. It's a reciprocal. That's not a linear relationship. So for example, this is the graph of 1 over x. Okay, it's not a linear line between negative line. It's sort of bows out like this. That's what the problem is for our linear texture mapper. So that's not a linear relationship between z and xs. Okay. However, we can do a little trick here. We can just turn it on its head. Okay, let's find the reciprocal of this expression. Okay, so z becomes 1 over z. Beta times f is 1 over beta times f. 1 over xs becomes 1 over xs. So in other words, just xs. And beta over alpha comes alpha over beta. So the trick is, if we consider the reciprocal, which is just 1 over that quantity, we now have a linear relationship in terms of xs. So we've gone from having a non-linear relationship, where it's not a straight line, to having a linear relationship. The problem is, we've got a linear relationship between 1 over z and xs. Okay, we wanted z and xs, but that's easy to do. Okay, so how does this link to texture mapping? Okay, so to apply the perspective projection while still using linear interpolation, we calculate the 1 over z value for our scanning streamer. So as well as x and y, we also calculate 1 over z. And we interpolate the 1 over z. Okay, so in the screen space, our scanning streamer, we also calculate 1 over z. In the texture space, to take that into account, we also divide by z. So instead of u and v, we have u over z and v over z. And then we just apply linear interpolation in the same way. So not only have you got x and v, you've got u and v, you've also got w in there. Okay, so we've got 3 dimensions in our texture, well, pseudo 3 dimensions, and we've got 3 dimensions in our screen space. Okay, so that's our screen space coordinates, so xs, ys, and 1 over z. Here we've got texture space coordinates, u over z and v over z. All we do is when determining what textile we have, we divide u over z and v over z by z to sort of convert it back. So what we do is we convert it, so we're dividing by z, apply all our linear interpolation. Now at the very end, when we want to decide what textile we're at, we then divide by z again to convert back. Okay, and that's called perspective texture mapping. Okay, and what the effect is it's easier to see if I'm going to go back to the demo in a minute. It has the effect of maintaining that sort of depth information. Right, so I just right, this time I'm going to do the same thing. So if I start off with the X pattern, I'm going to do it down the Y-axis, and this time I'm going to use perspective projection. You can see that that X is now no longer skewed. It's actually sort of looks like a straight line. Slowing down for a bit, don't know why, but okay. So what does that look like when I've introduced Killian back in? Okay, he's no longer skewed. Okay, so therefore it looks, you know, the photograph maintained. I mean, there's a bit of a fake sort of perspective going on. Sort of, I've enhanced it slightly just to overemphasize the point. Okay. And if interesting one is if we do the chessboard, and you can again see it's a bit blocky because I've reduced the number of pixels, but you can see it sort of works. Okay, so linear texture mapping is no good. It's not used because it doesn't take into account depth. Perspective texture mapping takes into account depth, and therefore it's used. If you're playing a game or something like that, go around a virtual world and they use linear texture maps, it looks weird. It just wouldn't look sensible. You'd be taken out of that sort of immersion. Okay, I'll slow it right down. But there we go. Okay, so we can see, but if you compare the two, it's difficult to compare static images. It's a lot easier when they're moving. So you can see the difference, and one's a lot better than the other. Okay, so that's texture mapping. It's not just use the texture. Okay, do you remember when did I do lighting? Was that last week? Yeah, lighting was last week. And I mentioned, okay, Phong shading. Oh, actually, you tell me. Can anybody remember how we calculate Phong shading? Okay, so Phong shading, what you do is you calculate the normal vectors at vertices and you interpolate vectors across the centre of a polygon. Actually, I was lying. Well, you can do it that way, but it's too slow. Faster way of doing it is applying what we call a texture map, called a Phong map. Okay, so what we have here is, this is a 256 by 256 texture map. And this relates to all the different possible shading regime using Phong reflection. So in the middle, you've got lots of reflection. Toward the outside, you've got smaller. And what fast Phong shading does is it takes your polygon and it calculates, okay, what's the equivalent vertices on this Phong map, and it applies this map to your screen space. So it's called fast Phong shading. It's actually a texture mapping technique. Okay, calculating all the normal vectors would actually be too computationally expensive. So we use what we call fast Phong shading. Okay, another application, and this is really nifty, it's called bump mapping. Now, remember when we're dealing with Phong reflection, the reflection, how it looks depends on where the viewer is. So as you move the viewpoint, you'll have different reflections bouncing off at you. Okay, so what we can do is, as well as applying an image using texture mapping, we can actually apply what we call a normal map. So we have a map of normal vectors, okay, called a bump map. And what we do is we use the texture mapping technique to apply our bump map to our polygon. So we've still got a flat polygon. It just so happens each pixel within that polygon has a normal vector from our bump map. So for example, let's say I wanted to model a curved surface. Okay, so there's my curved surface, but I've only got one polygon. Okay, so I've only got one polygon to actually model that curved surface. And if I've got one polygon, each pixel in that polygon is going to have the same normal vector. It's going to be pointed in the same direction. So when you apply lighting, that curved surface, as I move around, it's going to look like a flat surface. But what we can do is I can apply a bump map. So each pixel on my curved surface has a slightly different normal vector. So then when I apply my lighting model, okay, and I'm looking at my curved surface, it gives the impression of a curved surface. And this is called a bump map. There's a better example here. Okay, so imagine you've got like a cobbled street. Okay, so imagine you've got a virtual world or a computer game, you've got a cobbled road. You're not going to have to want to model each cobble using polygons. You just want one polygon for all the road. Okay, so then you apply a texture map. Go out and take a photograph of some cobbles. That's what we have there, and we can just apply that. Okay, but that tends to look a bit sort of fake. Okay, back in sort of 90s and early noughties, before bump mapping really came in. Okay, you'd have texture mapping, but it didn't look quite realistic. So in addition to the texture map, you can also have a bump map or normal map. So here we have, you take your texture and you define some normal vectors. Okay, so I just explained the colors. Any vector pointing to the right is given a red color. Vectors pointing sort of up in the y-axis is given a green color. And vectors pointing out towards us is given a purple color. You can see here that the top of these cobbles, so this region there, the vectors are mainly pointing upwards, not out. And on the right-hand side, they're mainly red, so they're pointing to the right. So this is a texture map of normal vectors. Okay, so if we apply the texture and that normal map, that's what you get. Now I can't show it here, but as you move around, the speculative reflection and the diffuse reflection would change because you're moving your viewpoint, and then it gives you the impression of that being a textured cobbled